Welcome back, everybody. So we're going to be talking about, we're brushing up where we left off. So theorem 1.2.2 was that if your functions are all equal to each other, except possibly at the value in question, the x value in question, a, then the limits are the same. Basically, what we were trying to explain last time, what we were talking about, was that you can algebraically manipulate something like this. You can factor the bottom and cancel the common factors. And normally we just write that's equal to x, 1 over x plus 5, like we have here. But technically speaking, if we wanted to be really, really pedantic, we would write provided that x does not equal 5, because this function, like this expression and this expression, do give you the same values for everything except for 5. If you plug in 5 into the first version, you'll get 0 over 0, which is undefined. It's indeterminate. Whereas if you plug in 5 here, you get 1/10. So they are the same expression, they're the same function everywhere except at -5. Or sorry, except at 5. So that's the reason why this theorem is so important. It allows us to algebraically manipulate equations and still get the same limit. So if we're given a limit and we get 0 over 0, we can algebraically manipulate, we can factor, we can multiply by conjugates, all that fun stuff, and get the same answer and get the correct answer. So that is what we're going to start seeing here. So the tried and true one we've already kind of experienced right here is factoring. So let's try to do this limit by just plugging in the value. Right? So try x equals 3. And I guarantee you, though, if you do that, you're going to get 0 over 0, which is an O damn. Or an O dip, if you're what's it called? If you're a Good Place fan, or oh no, whatever you want to do. Or if you have a child, a toddler specifically, you just go, oh no, it's broken. Which every child goes through that stage, apparently. Oh no, it's broken. Despite them breaking it. Oh no, it ripped. No, son, you ripped it. Anyways, so that tells us that we need to do something. So we're going to factor it. Now, I want you to write this the way, like, we're going to be very, very particular if you're going to see the notes down below. So we're going to write the limits as x approaches 3, and we're going to factor these things. Now, you can do it by hand, absolutely, but we have something kind of unique at our disposal when we're doing this. Because when we plug in 3, we got 0 and 0. That means that x minus 3 is a factor. There's that theorem from pre-calculus, the factor theorem, that if f of 0, like f of c equals 0, then x minus c is a factor. Do you guys remember that theorem? Not really. It's okay. What it's like, just on the side here, if inside one land, if f of c equals 0, then x minus c is a factor. So what I'm trying to explain here is that you could go through and do, like, now these ones aren't too terrible, right? But what if this was like 42x squared plus 33x minus 180? A lot of things to try and go through before you actually find the factorization. Whereas if you know that it's going to be 0, then you can just write that factor and go on your merry way. So you can just write this. Okay, so we know that x minus 3 is going to be one of the top. And we know it has to multiply. The first two need to multiply to x squared. The last one needs to multiply to -18. So the next factor is going to be x plus 6. Now, does that help us here? No, because we can probably factor this pretty quickly. But just saying, if you know that it's going to equal 0 for both the polynomials, you know that x minus that number is going to be a factor. X squared minus 9, that's a difference of squares. So we write this as x plus 3 times x minus 3. And lucky for us, the x minus 3's cancel. And we've got the limit then equals the limit as x approaches 3 of x plus 6 over x plus 3. And now that we've canceled something, we should try and plug in. We've simplified the expression inside the limit. So let's try and plug in 3 again. If we get a number, we got it right. If we don't get a number, then we need to do further algebra, whatever that may be. But for us, that's going to work out. We're going to get 3 plus 6 over 3 plus 3. That's going to be 9 over 6, which we should simplify to 3/2. So you'll see that on my exams, by the way, on the front page. I say, please simplify nice values. So please don't leave it as the square root of 4, write it as 2. If you got 9/6, please write it as 3/2. If it's 91 over, or 9,155 over 25, don't worry about simplifying it. I mean, your calculator can probably do it for you, but don't worry about simplifying too much. But if it's something that you can do in your head, please, or do quickly, please take care of it. Now I want to talk about this method that we did here and the specifics in the writing of the mathematics. So a lot of students notice that we didn't drop the limit sign until this stage. Once we had plugged in the value, that is when we dropped the limit. And there's a reason for this. Limit as x approaches 3 of x squared minus 3x minus 18 over x squared minus 9. That is a value. This is a value. Whereas this right here is an expression that varies based on what x is. So you cannot just drop the limit sign midway through, because then you're saying a value is equal to an expression, which is not correct here. So you do not drop the limit sign until later on. You do not drop the limit sign while you're taking the algebra. And then the question that's natural that comes after is, well, then when do I drop the limit sign? Phil, when do I drop it? It's a great question, and I'm glad you asked, Dylan. So the answer, of course, is that you write that when you have actually plug in the x value, when you can plug in the x value. So the way I like to think about it, if you're ever confused, is think about square roots, right? Right. If we have the square root of 4, actually, let's make this a little bit more important. So we have the square root of 3 plus 1. We don't drop the square root sign right now, right? We simplify the inside. We write this as the square root of 4, and then we write 2. We dropped the square root sign because we took the square root. Right? We don't and we don't write square root again, right? We don't write another square root at the end of it. Right? We don't do this. We don't do that because we've taken the square root. So we need to know when to stop writing the limit. We stop writing the limit when we've taken the limit, which is when you plug in the value. So going back up here one more time, and don't worry if you don't have it written down, we can go back. I dropped the limit sign precisely when I was able to plug in the x value. I didn't drop it beforehand. And if you do mess this up, I will have to mark you down for for not being mathematically valid. And I know that can seem harsh because you're saying, but I got the right answer. And my response to that would be, imagine on an exam, on an essay, you could have the most perfect argument for your hypothesis or whatever for your paper, but if you make a bunch of spelling errors, your teacher's going to dock you some points there, right? Same thing in mathematics. We want to present a mathematically valid argument, and if you drop the limit sign, you're claiming things that are equal that aren't equal. So any questions on that? Yes.
So after you factor both the numerator and denominator, is it okay to just go straight into plugging 3 in instead of writing limit as x approaches 3. What's it? X plus 6 over x plus 3.
Excellent question. Sorry, what's the name?
Hector.
Hector. Hector has a great question. So he's asking, can we go straight from here to here, here, or here? Absolutely, for me, that's fine. I'd like to see it be plugged in just when we're starting out. Later on in your, like later on this semester, you can kind of drop that stuff. But if you know what to do here, like you know that these are just going to be ones now, they're canceled, so they're not there. So just 3 plus 6 over 3 plus 3. If you want to skip writing the step, absolutely, be my guest. I'm just writing it for completionist and for if a student wants to see more steps. But you can absolutely skip steps as long as it's like not a huge jump in logic. Yeah. Any other questions? Great question. Great question. All right. Another way would be for finding common denominators. So the limit as h approaches 0 over 1 over 4 h plus 4 minus 1/4 over h. First thing we should always try and do is try to plug in the value. So try h equals 0. But if you're going to do that, you're going to get 0 over 0 because you're going to get 1/4 minus 1/4 in the numerator. That's 0. And then 0 in the denominator. 0, 0. That's an oh no. It's broken. So what are we to do? Cry. Say it's impossible. It's like the Yang-Mills existence and mass gap problem. It's unsolvable, right? Or it hasn't been like it's one of the $1 million math problems, right? No, it's not. We know that whenever I give you a problem in this class, there's going to be some way to solve it. I'm not going to be my my real analysis teacher in my senior year of college who put the Riemann-Zeta hypothesis as an extra credit problem. I'm not going to do that. Just a fun small aside. So my teacher, he gave us our exam and he said, now I've put an extra credit problem on this thing. Do not answer it unless you have completely finished the exam and are happy with everything. Do not answer it at all unless you're completely satisfied with everything else on your exam. Then start attempting it. And then he posted the solutions and said, this is the Riemann-Zeta hypothesis. If you had figured it out, you would have gotten a lot of fame. He might have stolen it from you. Because that problem has been unsolved for 200 years, something like that. So anyways, point being is there's always a way to solve the problems that I'm going to give you. I'm not going to give you an unsolvable problem. So what we're going to do is, as the technique suggests, we're going to find a common denominator. So we're going to write this as, I mean, you can write it on the thing itself, but I want a little more space. So this is limit as h approaches 0 of 1 over h plus 4. The common denominator here would be 4 times h plus 4. So the first factor is missing a 4 over 4. The second factor is missing an h plus 4. So we'll multiply its numerator and denominator by plus 4. Now we've got to make sure we know where the main bar is, right? So we're going to make sure it's very, very clear where the main bar is. But seeing as you kids are college students, that's not easy to know, right? Where the main bar is. Right? Drinking bar. Fun fact, I actually made that joke when I was applying for this job. Because in teaching jobs, you have to do a teaching demo. And I made that job. I made that joke during my job. I'm pretty sure that's the only reason why I got this job. So that's a true story. That's 100% true. But anyways, I digress. So like that. We'll simplify. And this is like, after you've shown like the initial step, if you want to skip some additional algebra, that's fine with me. But I'm going to show it for completionist sake. So we get 4 minus parentheses h plus 4, all divided by h times h plus 4 times 4. You could write this as 4h times h plus 4. Now, several students would ask, well, where did this h come from? So this part up at the top was going to become 4 minus h plus 4 over 8, h plus 4 times 4. But you got a second denominator, so I just combined the two of them. There's an additional step there, but if you want me to show it, I'm happy to show you. If anybody's lost on that step, please let me know. It's all right if you are. And I want to talk about something real quick. So John Doe student does this. It's a big no-no. You put the parentheses there. Put the parentheses. Please, please, please. I will rub your nose in it if you don't put the parentheses. Bad student. Bad. Bop your nose. Or do like the little thing behind the neck, right? That's what you're supposed to do, to nip the dog, right? Bad student. You gotta put the parentheses, otherwise you might remember, it's like, no, Phil, I got it. I got it. I know what I'm doing. Yeah, you probably do, but that you don't, like, you can't account for everyone else on the road, right? So maybe someone sneezes and it distracts you, like they do that really, really loud sneeze. Maybe someone comes in and it distracts you for a second, and then you forget that you didn't, like, that you were going to distribute. So please put it there so you remember to distribute. And that'll cancel the 4s, and we end up with the limit as h approaches 0 of negative h divided by h times h plus 4 times 4. And isn't that nice? The h's cancel. So we're just left with a -1 up top. So writing it one more time, but you can skip this step if you'd like. So limit as h approaches 0 of -1 over h plus 4 times 4. And now, looking at it, I don't foresee any issues coming in when I plug in 0 for h, right? Because I'm not going to get it to 0 in the denominator. Like my denominator is not going to be 0. I'm plugging in h equals 0. So 0 plus 4 times 4. So that should be -1 over 0 plus 4 times 4, which is -1/16. If you want to skip that previous step that I just wrote, you're more than welcome to do so. If you want to go straight from this to the answer, that's okay with me. And notice I dropped the limit sign once I plugged in h equals 0. Any questions on that? On any of the algebra or anything like that? Do you understand why I said in the very first day, algebra is the hardest part of calculus? Because there's so much algebra going on in the background. And this, they can get much more complicated than this. So, yeah. Okay. The other technique is conjugates. You guys remember conjugates? So just as an aside up here, if you've forgotten, so A plus B and A minus B are what we call conjugates. If you have two binomial things, and the only difference is the sign in the middle, plus and minus, they're called conjugates. Why do we care about conjugates? Or conjugation, the process of multiplying by conjugates? It's that when you have, so why are they badass? Well, because if you multiply them together, a plus b times a minus b, you get a squared minus b squared, which is a big deal. That makes it so that if I multiply by conjugates of square roots, they get squared, and then that square root goes away. So that's the reason why conjugates are very, very useful. They're also useful in complex numbers, where they can turn anything, like they can take two imaginary numbers, two complex numbers, and you multiply them together, and now you got a real number, which is pretty wild, pretty nuts. So conjugates are very, very, very good. And a very, very useful tool. Mathematicians use them all the time. I like to think that in mathematics, there's like several tools that you like can't live without. Like you get a tool belt as you go further on in mathematics. Like you get your screwdriver, your wrench, your Allen wrench set, and all that stuff. And one of those tools is multiplying by conjugates. One of the most common ones we learn is multiplying by 1, right? Cleverly multiplying by 1, which we did just here. Cleverly multiplying by 1 4 over 4 is 1. So that's one of the first ones we learned, but there's many more. Conjugates are one of those things. So what we're going to do is we're going to multiply. We're going to first of all, try x equals 2. But you're going to get 0 over 0. Oh no, it's broken. And then we're going to multiply by conjugates to try and get rid of this. So square root of x plus 7 plus 3 divided by the square root of x plus 7 plus 3. And the reason why I wanted to mention this right here is to remind us that yes, you can, in theory, you can spend the painstaking hours of doing the foiling here, right? Foil these together. And you can write that down, but it's really unnecessary because when you multiply conjugates, you just square the first term and then subtract the second term squared. So all this is the limit as x approaches 2 of the square root of x plus 7 squared minus 3 squared, all divided by x minus 2 times the square root of x plus 7 plus 3. Now I'm writing this extra step. I'd ideally like you to skip this step and go right now to the next one. But just to show you how the conjugation process works. When you multiply two conjugates together, you just square the first term, square the second term, and take the difference of them. You can FOIL it out, but it's just putting more work on yourself. The more work you can do in your head, the better. Or the more work you don't have to write, because the more you write, the more chance you have of developing carpal tunnel, which we don't want. We all want to be able to play StarCraft into our 80s, right? Make sure we can click that finger as fast as possible. Get those, what is it? Movements per second. Is that like APM? Actions per minute. You want to get your APM up. All right. Man, retiring at homes are going to be very interesting later on. I feel like we're just going to have like LAN parties and stuff. It's going to be awesome. So this becomes the limit as x approaches 2 of x plus 7 minus 9, all divided by x minus 2 times the square root of x plus 7 plus 3. So what I would ideally like you to do is, so write that step in red that we did up top, and then just immediately go down to here. I'd like you to do that. I don't expect it. I'm not going to penalize you for writing that middle step. I'm just trying to get you to do these things faster so that you can go on your merry way on exams and spend more time on the harder problems. So you can also do this in my class. I'm fine with you doing this. So writing above this, well, this is going to be x minus 2. 7, like find like terms, you're going to x minus 2, and then those things will cancel. Boom. We're going to get the limits as x approaches 2 of 1 over the square root of x plus 7 plus 3. And now we're going to take the limit. We're going to drop the limit sign and plug in 2 because I don't foresee any issues. There's no subtraction going on in the denominator, so I don't foresee us getting 0 in the denominator anytime soon. So that's good news. So that's going to be 1 over the square root of 2 plus 7 plus 3, which is going to simplify to 1/6. Because it's going to be square root of 9, which is 3, 3 plus 3 is 6. Done deal. Though if you want to go straight from here, people watching the recording, if you want to go straight from here to here, you're more than welcome to do so. Go straight from here to here. That is okay with me. Any questions on that? Much better than guessing it numerically, right? Just plugging in numbers and just hoping it works. Now, granted, though, you can use that method here to verify your work. That's one of the things I like. So, like, plug in 1.999, right? You should get roughly 0.167-ish, right? 1/6 is 1.6 repeating. think so, yeah. So you can check your answer. That's what the point being is you can use the numerical guessing method to check your answer for the verified. Last one that we're going to talk about is the other category, which is unspecified. Now, simplification is always a good option. And then from there, that's when if you've tried factoring, if you tried conjugation, you've tried everything and nothing's working, try something new, right? Keep messing around with it. They're Legos. Built like mess around with them, put them together, put new pieces on it, see what happens. I don't care if they're not matching. You don't have to have the same color wing on the left and the right hand side. It's not necessary. So mess around with it. It's okay. So one of the things we're going to try t equals 0. But I guarantee you, if you do that, you're going to get 0 over 0. Darn. So what do? Well, that 4 plus t squared, maybe if we FOIL it out, maybe if we simplify it out, we'll get something better. John Doe student, so don't write this down. I'm writing this red, so you don't write it down. John Doe student writes this. John Doe student gets a 0 and a giant no on their paper. Why? They didn't FOIL yet. Yes, they didn't simplify it correctly. The squaring has to get FOILed, right? I'm just bringing that up because I hate seeing it. I hate seeing it happen to students making the freshman's dream mistake. So no, what happens is this becomes the limit as t approaches 0 of 16 plus 8t plus t squared minus 16 all over t. And so the 16s will cancel. You get limit as t approaches 0 of 8t plus t squared all over t, because the 16s cancel. Another mistake that John Doe student makes. John Doe student, or Jane Doe. Jane Doe student, she cancels this t like that. Why is that not feasible?
You have to factor up the numerator.
Exactly right. We need to factor. You cannot cancel terms. So right here, t is a factor in the denominator. It's the only factor in the denominator. But 8t is a term of a binomial set. So that 8t plus t squared, that's a binomial. And the 8t and the t squared, those are both terms. You cannot cancel terms vertically and diagonally. You can only cancel factors. So first we need to factor it. So we factor out a t, and we get 8 plus t, and then the t's cancel. And let's use a little bit of lavender, get a little bit of nice calming effect. Limit as t approaches 0 of 8 plus t, that's just going to be 8. Any questions on that? Okay. So extra practice. This is one for for this weekend when you're cracking open a cold one with your boys and your bros and your broristas, you know, your broristas and your braristas. Just one to bust out with your friends. So I think this will make you guys get closer as a friend group. I think this is the best way to bond. It's doing this type of a math problem. So definitely do this weekend. It's a really good problem. You'll be invited to all the parties when you do this. Okay. It's how I actually met my wife. True story. Not really. But point being, it's a good problem. I think you should try it. I think it's a really good one. And we if anybody has any questions on it, we can come back on Monday and talk about it. So with there's these 4 problems, right? Yeah. I'd like us to do these 4 problems. Go ahead and work by yourself or with the group, with your friend, with your classmates. They won't bite. but you don't have to, right? If you're like me, I didn't like doing that personally. But I'd like you to do the next 4 problems. I will slowly fill in details, and you can ask me questions while I'm just hanging out. Zoom out for these ones. You can feel free to jump around. Would you guys like the lights on? Would that be helpful while you're? Absolutely.
Oh, yeah. And times that. So the. So what if you multiply this? One plus three and then minus seven. And so then this cancels that. So one plus three. Yes, it's just here.
Which is very good.
So then.
This is a new, but. So, you will do it once you think. Once you put it.
My virgin. No, you're good. That's okay.
Good. We still have.
I have the answer to part A on the board if you'd like to check your work.
That's why
No.
so. This right here is still the same thing. Yeah. Why am I?
Now that you're going to ask. Oh.
It's one of them. And section one with this is higher. That's why.
Oh, all right. Well, then you're ahead. With this ambition, I guess.
And I guarantee that will lead to next. I still say there's one thing to set out.
Yeah. I had to really study that one. It's only one. Yeah, me too. I was. Oh, wait, this is.
Oh, yeah, for this problem. I decided. I noticed. My mind is what is 3, 1, minus 7. I decided to just. Why minus 7? So.
Yeah, no, I know exactly what the question is. So a couple people have asked this question and I'm glad we're asking it. So how did my y minus 2 just magically go in the denominator of the, like, so up in the top, just for a second, So I'm gonna turn it off for just a moment. Wait, just a moment. How did I go from here to here? So there's a little bit of in between algebra over here. This way. No. I sent my wife and I have both sent some very angry emails to Notability about this change. So what you end up with is y minus 7 plus y plus 3 all over y plus 3 times y minus 7 all over y minus 2. Now remember, y minus 2 is in the big denominator. So this is the big numerator up in the top, and then the y minus 2, that's in the denominator. So this is the same thing as y minus 2 over 1. And remember, dividing by a fraction, you flip and multiply. You multiply by the reciprocal. So then there's this extra step. This becomes y minus 7. And you could simplify it as this is going along, but and then y plus 3 all over y plus 3 times y minus 7 times 1 over y minus 2, which is how I arrive at that next step, by the way. Now, it's not wrong to leave it just as it is, and you can cancel it at the end anyways, but that's just the way I did it. All right. So this is some side note land. Side note algebra. Oh, sorry about that. And that's why I always have to, I flip my, because the home button is right here. So if I'm pushing my finger down, then it just puts me on home. Side note algebra. Okay. So back to where you guys were, and I'm going to continue helping. Let me just finish this one off, actually. And so continue working. We're going to take a break here in just a moment. Okay, I had some questions. I'm sorry if I missed somebody. This person had a hand. I don't know who it was.
Like so you need like you to be asked to drop the problems. That's when you get to live last.
Yeah.
So you are you need to skip data right. The next step. Yes. So, Robin there. Love the idea. Love the idea. It's very close to being correct. But that would be multiplying by something that's like multiplying the expression by something new. And you can't sheet roots. So you could do this, but you also have to multiply by y plus 3 times y minus 7 with non as well. You have to cleverly multiply. But there is a method that I'm actually going to mention. I didn't mention that. So I'll talk about that.
Thanks.
Yes, of course. Okay, we're gonna take a little break here. If you want to continue working, go right ahead. We're gonna take a small breather and come back. Just in the interest of time, we're gonna only do a 5-minute break. I'm sorry. I lost track of time. So we're gonna come back at 10:21. People watching the recording, go ahead and take a break. So I want to go over all of them and then also talk about an alternative way to answer or to do the algebra for part B, the first 2 problems. So for the first one, we'll look at it, try and plug in x equals -5, and you'll see that you get 0 over 0. That means, and you can factor it by hand, absolutely, that's fine. Or you can know that because x equals -5 made the numerator and the denominator 0, that means that x minus -5 or x plus 5 is a factor. So you get x plus 5 times x minus 7 over x plus 3 times x plus 5. And don't forget your limit sign every single time until you're ready to drop the limit. Just like with square roots, you don't drop the square root early. While you're simplifying the inside, you keep the square root there until you're finally ready to take the square root. Same idea. So we cancel the x plus 5s, you get limit as x approaches -5 of x minus 7 over x plus 3. Oop, no, I wanted to be using the pointer. And that we can plug in -5 into and find no issues. You'll get -5 minus 7 over -5 plus 3. That gives you -12 over -2, which we simplify to +6. On the second one, we kind of already talked about the algebra that was going on, but I wanted to mention and we'll get to the same section. But an alternative way to do this. So what we do, we call this right here, this 1 over y plus 3 plus 1 over y minus 7 all over y minus 2. We call that a complex fraction. Because it's got fractions within fractions, a fractionception, which is not nearly anymore. That's not funny anymore. That used to be funny when Inception was a thing, but Inception's been 10 years, I think, since that movie came out. Whatever, doesn't matter. Point being is it's a complex fraction. Now there's 2 methods to solve a complex fraction. You can, or to simplify, not solve it, simplify it. You can either take care of the numerator and the denominator separately, which is the way I did it originally. That's the way that most people know how to do it. But I also have a video on this in the Math 96 refreshers in the algebra section on complex fractions. There's a second method where you look for the common denominator of everything. So the common denominator of both the numerator fractions and the denominator fractions. So there's no fractions in the denominator, right? It's y minus 2 over 1. Like there's no fractions in the denominator. There's fractions in the big numerator right here. So the least common denominator of everything is just y plus 3 times y minus 7. So you can multiply the big numerator and the big denominator by the LCD of everything, and then distribute it in. When you do that, when you distribute it into the first term, the y plus 3's cancel, and you're left with that y minus 7. When you distribute it into the big numerator of the second term, the y minus 7's cancel. You're just left with the y plus 3, and then the denominator, nothing cancels. So you just get y minus 2 times y plus 3 times y minus 7. It's a much faster way, and that's the way I'm partial to doing things, but I realize that not many people learned that method. So if you want to learn it, complex fraction video talks about method 1 and method 2. My voice will probably sound a little bit more skippy. This was I made that video about 4 or 5 years ago. Been coasting on it ever since. But yeah, so if you want to learn more about how to deal with complex fractions, please watch that video or look up complex fractions on YouTube or something like that, and you can find plenty of videos on how to simplify it. So when we get to that point, no matter what, we get this. And so we cannot cancel the y minus 7s or the y plus 3s because right now in the numerator, because they are joined together by a plus, the y minus 7 and the y plus 3, those are terms right now in the numerator. So they cannot be canceled because they're not factors. But we can combine them. We can combine the y's to get a 2y, and the negative 7 plus 3 gives me a minus 4, which we luck out because then that means that you can factor out a 2 and you get 2 times y minus 2. And luckily for us, that means that the y minus 2's cancel. So you're left with the limit as y approaches 2 of 2 over y plus 3 times y minus 7. Plug in 2, you get 2 over 5 times negative 5, which gives you that negative 2/25 at the very, very end. Any questions on A or B? These first two. Okay, second two, the first one, try plugging in t equals 6. I guarantee you will get 0 over 0. So that means we just need to factor it. And luckily for us, the first one is what we call a perfect square trinomial, which you don't need to know that name it terminology, but just that's what it is. It's t minus 6 times t minus 6, or t minus 6 squared, however you want to write it. I factored out a t from the original, from the beginning. I'll even write that step here. So there's a t that can be factored out. And then we get t times t squared minus 36. T squared minus 36 is a difference of squares. So that factors to t plus 6 times t minus 6. And then you can cancel one of the factors of t minus 6. And you get the limit as t approaches 6 of t minus 6 over t times t plus 6 right here. We're going to ignore that my voice cracked there. And then now that we've factored something, we're going to go ahead and try and plug it in. If we still get 0 over 0, that means we need to do more, but I'm pretty sure we'll be fine. You get 0 up in the numerator divided by 6 times 12. And a lot of students will want to think like, oh no, that's bad. That's fine. 0 in the numerator, totally chill. 0 over a number, totally chill. Because 0 divided by anything is 0. So we write our answer, which is 0. Last one here. It's got a radical. First thing you should think about when dealing with radicals is, man, I hate dealing with radicals and I want to get rid of it. So you'll multiply by the conjugate. And when you do that, so this is the square root of 3x plus 1 minus 4. So the conjugate of that, the only thing that changes is the middle sign becomes the opposite. So instead of a minus sign, it's now a plus sign. Had this been a plus, we multiply by a minus. So just remember the conjugates, they have to work that way. Conjugates, you just flip the sign in the middle. That's the conjugate. Change the sign into the other version. Then you could FOIL it out, but you could also just remember that a square, like when you do that, it just squares the first term, squares the second term, and takes the difference. So squaring square root of 3x plus 1 gives me just 3x plus 1. Squaring 4 gives me 16. Taking the difference, you get that. And then in the denominator, you still got that x minus 5 times the square root of 3x plus 1 plus 4. Now, luckily for us, when we combine like terms here, we get 3x minus 15, which has a common factor of 3, which we can pull out front. So we get 3 times x minus 5. The x minus 5s cancel. We get to here. The limit as x approaches 5 of 3 over the square root of 3x plus 1 plus 4. And then we can plug in the value and we're all gravy. We're all good. Plug it in. You get 3 over the square root of 16 plus 4 or 4 plus 4, so 3/8. And that is our answer. Any questions on that? Okay, which comes to one of the cool theorems, the squeeze theorem. Squeeze theorem. Let f, g, and h be functions such that f of x is less than g of x is less than or equal to h of x for all x near a. Doesn't need to be for all x, but just when you're local, when you're around the x value a, all your functions need to be sandwiched that way. Then, if the limit as x approaches a of f of x and the limit as x approaches a of h of x both equal L. So the outer function's limits. So the lower bound function and the upper bound function, if their limits at a are both L, then by necessity, the middle function's limit also has to be L. And so one of the ways that you can kind of visualize this, I've drawn a graph here. So let's draw the three different functions. Let's make h into the quintessential calculus graph, like this. That's going to be h of x. Let's make a tick mark here for a. Let's make g of x be a straight line that touches h of x right at a. So we're going to make g of x look like this. Oh. This is g of x. And then last but not least, h of x, we'll just make it into a parabola. If I said anything else, I meant f of x. So I don't know why. And I hope this kind of visualizes, like, so the proof of it is a little more convoluted, but a visual proof, picture's worth 1,000 words. So we'll just use that. When you look locally at this graph, oh, and then here's the value L right here, by the way, where that point is. When you look at it zoomed in, because it's sandwiched in between them, there's no other option for it to do, like for it to be. It has to be the same value. If they all go to that same limit, if the upper bound and lower bound both go to that same limit, then the g is forced. That's the idea of the squeeze theorem. How useful is it? Not really. Not very. The only thing it gets useful for is the important limit, which we'll do in a second. So we'll do this example. If 3x is less than or equal to f of x is less than or equal to x cubed plus 2 for all values between 0 and 2, find the limit as x approaches 1 of f of x. So we write 3x is less than or equal to f of x. It's less than or equal to x cubed plus 2. Now, if you remember from section 1.1, I was saying there's a different way to write a limit. You can write it with just arrows, right? So what we're going to do is we're going to notice as x approaches 1, what does 3x approach? 3. If you can plug in the value of the limit and get a number, that's going to be the limit. So as x approaches 1, 3x will approach 3 times 1 or 3. As x approaches 1, x cubed plus 2 will approach 1 cubed plus 2, which is also 3. So the upper bound and the lower bound functions both approached 3 as x approached 1. So by the squeeze theorem, the limit as x approaches 1 of f of x must also be 3. There is no other way for it to be. Oh, so you recognize that as a rectangle. You recognize that monstrosity as a rectangle, but when I try and draw one perfectly, you don't recognize it. Sure. Now that's a very, very constructed example. That was very, very, I made it that way. But let's look at some other ones. So use the squeeze theorem to determine the limit as x approaches 0 of x times sine of 1 over x. So one thought would be, okay, well, we know from 1.2 that you can split a product into multiple pieces. But the problem here is that, and we learned in 1.1, that sine of 1 over x, that limit as x approaches 0 does not exist. So that's the issue. If you go back, way back in these things. The supposition is the terminology. The supposition is that the limit as x approaches a of f of x and of g of x, they both exist. So in order for all these rules to work, the limits of each piece need to also exist. And as we saw in section 1.1, this guy's limit, or girl, this girl's limit doesn't exist. So because the limit as x approaches 0 of sine of 1 over x dne, which breaks the suppositions of theorem 1.2.1. But either way, the trick though is note 2. Very, very useful thing from trigonometry. As many facts that we know about sine, the cosine, tangent, and cotangent, and all those fun functions. But one thing in particular that's very, very useful is that sine and cosine, particularly, sine and cosine are bounded between one, sorry. I'm going to make this sine of a blue box. Sine and cosine are bounded by 1, -1. Sine can never be larger than 1 and never be smaller than -1. Same thing with cosine. And it doesn't matter what's on the inside. Sine itself can only produce values between 1 and -1. So that means, and -1 is less than cosine of a blue box. So that means that -1 is less than or equal to sine of 1 over x is less than or equal to 1. Sine of 1 over x is bounded between those two values. Now, how does this help me? Well, that's looking awfully close. Looking awfully close to my limit in question. All I'm missing is an x. But what if I were to multiply this entire equation by x? Well, then I would get -x is less than or equal to x sine of 1 over x is less than or equal to x. Now, if there's any secret mathematicians out there, if there's any secret teachers from CSN, the math teachers that I haven't met, I guess, or someone from Nevada State or something like that, I know, technically speaking, when you multiply, like we don't necessarily know if x is positive or negative, which would affect the changing of the direction of the inequality. But because it's at 0, like because of it's the -1 and 1, we're fine. Just know that we could do this for this situation, because if x were negative, it would just end up flipping everything, but everything would work out fine. That's the reason why we can do this. So by a similar fashion, we're trying to find the limit as x approaches 0. As x approaches 0, -x will approach 0, and so will x. So by the squeeze theorem, this also has to be 0. And that's just a tricky one. The more important thing, by the way, that's how I'm trying to kind of gloss over it and move on to the other stuff, is I want to get to the special limits. This one right here, specifically the limit as theta approaches 0 of sine theta over theta equals 1, and the limit as theta approaches 0 of 1 minus cosine theta over theta is equal to 0. Part A, by virtue of the fact that this is equal to 1, if you make it the reciprocal, flip it, it also equals 1 as well. And the proof of that is something that really hurts me. So when I originally wrote these notes, I was writing them in Word. And I don't know if you've ever tried to use math equations in Word on a Mac. If you add too many things, it starts to get wonky. So I made this beautiful, beautiful proof of that. And I was going to put it in the notes. It was excellent. I was so pleased with that. I made a bunch of graphics. It was excellent. And then Word did what Word does best, and it just wiped it all out and made it so like some pieces were getting rid of it. So that's why it's not in here. But if you want to see a proof of it, I'm happy to show it to you at some point. Just not right now. You do not need to have this one memorized, but this one I would like you to have memorized. Specifically, there's an application of it later. So this one, find the limit as x approaches 0 of sine of 3x over x, or state that does not exist. Now notice the special limit said the limit as theta approaches 0 of sine of theta over theta. Not sine, what did I make that? Not sine of 3 theta over theta. So that's a problem. That's a problem. Because the special limit says theta over theta, sine of theta over theta, not sine of 3 theta. So what are we to do? Well, we do a little bit of the hand waving, a little bit of jazz hands. What we're going to do, so I'm going to take this sine of 3x over x, and we're going to multiply it, cleverly multiply by 1. We're going to multiply by 3 over 3. And the reason for that is then we get the limit as x approaches 0 of sine of 3 times sine of 3x divided by 3x. And now, granted, it's the limit as theta approaches 0 of theta over theta. But we're closer, right? Now it's sine of 3x over 3x, but it's as x approaches 0. However, I'm going to claim that this goes to 1. And the reason for that is as x goes to 0, 3x will also go to 0. As x goes to 0, 3x also goes to 0. So it works out. And in fact, there's a theorem on the next page that actually becomes a much better, much more versatile use of this. So suspend disbelief for just a moment, and then we'll have a theorem to take care of this in general. This becomes, we're going to take the limit. So this becomes 3 times 1, just 3. The reason for that is going to be the following theorem. Don't worry, I'm going to come back to this section. So if you don't have it written down, it's all right. We get out at 10:15. That's right. There's a guy out there, the next teacher, he's like giving me the stare down, stressing me out. All right. So theorem 1.2.4. If the limit as x approaches c of f of x is equal to 0, and c is never 0 around x equals c, that's just some filler information. You're never going to have to worry about that situation. It's always going to work out for us. Then the limit as x approaches c of sine of f of x over f of x is equal to 1. So as long as you've got like the same thing on the inside of the sine and the same thing down the bottom, and that thing goes to 0, you're all good. So for example, this one right here, the limit as x approaches 1 of sine of ln of x over ln of x. It's the same thing, and as x goes to 1, ln of x will go to 0, right? Because ln of 1 is 0. So this will just equal 1. So a very, very useful theorem that if you have sine, and you can use this as fact. As long as the inside of the sine, like the sine of the inside, like the inside is the same thing as in the denominator, it's just going to equal 1. But the problem there is that you need to make sure that they're the same, and that thing goes to 0 as well. That's going to be key. So going back to the previous one, that's why we multiplied by 3. Sine of 3x over 3x. As x goes to 0, these things both go to 0. Hence, that's why it's 1. So let's do another one of those first. This one right here. Let's do this one here. We're jumping around a little bit, but limit as t approaches 3/2 of sine of 2t minus 3 over 2t squared plus 5t minus 12. If you try and plug it in, as you always try to do, I guarantee you're going to get sine of 0 over 0, which is 0 over 0, which is an oh no. So what we're going to do instead, what should we do? Try and factor. Yes, try and factor the denominator. Always a good option. If at first, if you're if you're stuck on what to do, have you tried factoring? Have you tried doing some type of algebraic manipulation? And that's actually going to be what's going to save us here. The limit as t approaches 3/2 of sine of 2t minus 3. And wouldn't you know it, this thing factors to a 2t minus 3 times a t plus 4. Isn't that nice? So it wasn't like the Yang-Mills existence in Max-Scat problem. It wasn't the Riemann-Zeta hypothesis. There is some way to solve it. So in particular, I'm just going to rewrite this. You can skip this step if you want, but I'm going to rewrite this as the limit as t approaches 3/2 of sine of 2t minus 3 all over 2t minus 3 times 1 over t plus 4. As t approaches 3/2, this function that is both inside sine and in the denominator, it goes to 0. So that part of the limit will just go to 1 by the theorem above. This goes to 1. And then this part right here, you can just plug in 3/2. Remember, we talked about limits is the limit of a product is the product of the limits, as long as they exist. So this you can plug in, and then you can plug it in here. That'll go to 1 over 3/2 plus 4, which the 3/2 plus 8/2, 11/2. That's 1 over 11/2. That's 2/11, right? So this becomes 1 times 2/11 or just 2/11. I've seen plenty of students do this, by the way. They just take this and say this goes to 1, and that's fine with me. You can write that and then just write another step. But either way is fine. Do you see how this theorem gets used? It's okay if you don't. We've got plenty of other practice ones. The point is, you need the sign of the same thing in the numerator and the denominator. So that's why I isolated it from the other piece, so we could deal with it. All right. Let's do this one, because this one's far more useful, far more fun. And this will be the last thing we do. So sine, limit as y approaches 0 of sine of 2y over sine of 5y. Plugging in y equals 0, you'll see that you get 0 over 0. And I'm sorry, I'm going a little fast. I realized that, and I don't try to do that often. I got a little bit, I lost track of time. Try not to have that happen, but you're going to try y equals 0. You get 0 over 0. So the problem, though, it looks like a special limit. But it doesn't have the y's, right? Doesn't have the y's that we want. So one thought would be, let's multiply by 1 over y over 1 over y. Why not? Well, then you get sine of 2y over y, big bar, sine of 5y over y. We're getting closer. But we're not there yet because that's not sine of y, that's sine of 5y. So we're gonna do what we did in that first problem. We're gonna cleverly multiply by 1 again. Multiply by 2 over 2 in the numerator and multiply by 5 over 5 in the denominator. Because if we do that, we get the limit as y approaches 0 of 2 times sine of 2y over 2y all over 5 times sine of 5y over 5y. And as y goes to 0, 2y and 5y, the insides of the signs, will also go to 0, thereby obeying our formula, our theorem from the next page. So this numerator piece, this goes to 1, and so does this. So we just end up with 2/5. All right. Sorry to make that quick one. We can definitely come back. Please try to do that one with your friends this weekend. Crack open a cold Mountain Dew. As I'm assuming that was what they mean by crack open a cold one. That's what I've heard people say. It's a Mountain Dew, if I remember correctly. So crack open a cold Mountain Dew. Do that problem. That's the actual practice. Have a great time. If you have any questions, please feel free to email me. Otherwise, you guys have a great rest of your day and a great weekend. Yes. Yes, I do. What?
My homework is essentially.
Yes. Oh,